This video is the second in a playlist on waves and deals with the basics of waves. We'll discuss the following in this video: transverse versus longitudinal waves, which are the two basic categories that waves fall into, basic wave concepts and terminology such as the amplitude, frequency, wave period, and wavelength. We'll discuss the concept of wave speed and the derivation of the wave equation, which connects wave speed and frequency and wavelength. And finally, we'll talk about displacement versus distance and displacement versus time graphs. Just a note of caution before we get started. Much of this material may be familiar to you from your earlier studies, for example GCSE physics, and you may think it's rather easy stuff. In my experience though, many A-level students have a rather poor conceptual understanding of waves, and often don't move much beyond a GCSE level way of thinking and talking about waves. Throughout this video, we'll be using some simulations as an aid to develop a solid conceptual understanding about waves, and I'll also pose a couple of questions to help you reinforce your understanding. Waves fall into two basic categories: transverse or longitudinal, which differ in the direction of the vibrations relative to the direction of travel of the wave. Here, we see a wave on a string moving to the right. But notice how the green and red particles, which make up the string, are vibrating vertically up and down at 90 degrees to the direction that the wave is moving in. This is thus an example of a transverse wave. So we've just noted the definition of a transverse wave and also listed some common examples. For longitudinal waves, such as this sound wave that we are seeing here, the situation is different. You can see that the wave is traveling up, and if you focus on a single blue circle, which represents a single air molecule, you can see that it vibrates up and down. So the vibrations of the particles in a longitudinal wave are parallel to the direction of travel of the wave. Again, we've just noted the definition of a longitudinal wave and recorded a few examples of some common longitudinal waves. There are in fact waves that possess both transverse and longitudinal character, such as surface water waves. While this goes beyond A-level physics, I encourage you to do a little bit of research if you're curious to learn more about them. In the Intro to Waves video, we saw a triangular-shaped wave pulse, something like this. In contrast, if the grey rod doesn't just move up and down once, but rather continuously and periodically vibrates up and down, like you're seeing, we see a periodic wave that travels to the right. Such periodic waves are what we'll be focusing on here, and mostly throughout this playlist when we refer to waves, we really mean periodic waves. Focus your attention for the moment on the green particle on top of the rod. As it moves up and down, we say that it undergoes a displacement from its equilibrium position, which is the position it would be at if the string were undisturbed and there were no wave. Right now, the green particle is at its equilibrium position, and so its displacement is 0. When above the equilibrium position, its displacement is positive. When below, it is negative. Remember that displacement is a vector quantity, and we're choosing the upward direction to be positive. The maximum distance the particle ever goes away from equilibrium as it oscillates, its current position now, is known as the amplitude. Let's show this on a diagram and jot down some definitions. Again, focusing our attention on the green particle at the left end, we can see that it moves in a periodic or repetitive fashion. Starting from its initial position of maximum displacement, the particle eventually returns to its initial position. We say that the particle has completed one cycle of vibration. The time taken for it to complete one cycle is known as the time period, or just period for short. An important related quantity is frequency. The frequency tells us how many cycles the particle goes through per second. To calculate the frequency, you just do 1 divided by the period, expressed in seconds. From GCSE level, you may be familiar with the frequency being described as the number of cycles of the wave passing a point per second. I encourage you to drop that description and take up the A-level description I mentioned. Let's jot all of this down. One thing I want to point out here is that the units of frequency is the hertz, and the hertz, Hz, is equivalent to the reciprocal of a second, so a second to the power of -1. Alright, so here's a quick question for you. We're back to looking at the simulation that we've been viewing throughout the video, except I've just made a slight tweak where I've bumped up the frequency to 2 Hz. It was previously at 1.5 Hz. Now, if we look back at this green particle all the way over on the left here again, it's currently at its equilibrium position. Can you please try to work out how long we'll have to wait in seconds for the green particle to next return to its equilibrium position? That is once I press play. Pause the video and have a little think about this, and once you're done, unpause it and we'll discuss the solution. Alright, so clearly to work this out, what we're going to have to do is we're going to have to work out the time period, right? And that's easy. We just take the frequency, which is 2 Hz, and do 1 divided by 2 to get the time period, so 0.5 seconds. So that's the time taken for this green particle to perform one whole cycle. So in other words, starting from here, it's going to take half a second for it to move down, all the way down to its position of minimum displacement, and then back up again, all the way to its position of maximum displacement, right, and then back down to its initial position. So the time taken for this green particle to return to equilibrium is going to be half of half a second. In other words, 0.25 or a quarter of a second. So far, we've only talked about the green particle at the left end. However, you'll know or may have noticed that everything we've discussed holds true for any of the other particles. So for this green particle over here, it oscillates or vibrates with the same amplitude, period, and frequency as the green particle at the left end. Basically, the periodic motion of the grey rod and green particle at the left end gets copied by all the other particles. Looking at a snapshot of the wave, we see points of maximum displacement known as crests or peaks, and points of minimum displacement known as troughs. As you can see, I'm using the letters C and T to abbreviate crest and trough respectively. All the particles at crests move in step with each other. They have the same displacement and move with the same velocity at all times. This is also true of all the particles at troughs. They move perfectly in step with each other. To move in step is technically known as being in phase, and we'll discuss the concepts of phase and phase difference in a future video in the waves playlist. The minimum distance between two particles that are in phase with each other is known as the wavelength. We use the Greek letter lambda to represent the wavelength of a wave. You can see that two neighboring or adjacent crests are separated by a wavelength, as are two neighboring troughs. You can think of the wavelength as being how far we have to move to go through one cycle in the repeating wave pattern. Let's make a note of the definition of the wavelength. The concepts we've been discussing in this section, namely amplitude, frequency, wavelength, and so on, apply equally well to longitudinal waves as to transverse waves. There are, however, some concepts that we'll discuss now that are unique to longitudinal waves. Chances are you'll have met compressions and rarefactions before, and all you need to appreciate about them is the following. Given a longitudinal wave moving up, for instance, there will be regions known as compressions. Such regions are characterized by the particles having an increased density, or being squashed closer together, relative to the equilibrium density that would exist if there were no wave. On the other hand, regions known as rarefactions consist of the particle density being lower than the equilibrium density. A wavelength separates neighboring compressions and neighboring rarefactions. Let's now turn our attention to the concept of wave speed and the wave equation. Returning to the simulation, it's probably obvious to you that as the wave travels to the right, the overall pattern of disturbance shifts to the right as well. This is seen most clearly if we evolve the simulation in super slow motion. You can see the crests and troughs moving right. The speed at which they move is known as the wave speed. Let's make a note of this. Let me also reiterate a point I made in the first video in the waves playlist. When we talk of the wave pattern shifting, say, to the right, it's important to remember that particles or matter do not transfer to the right themselves. However, it is true to say that we can think of the wave speed as the speed at which the energy transfers. And this concept of transfer of energy is something I discussed in the very first video in the playlist. Before we derive and discuss the wave equation, let me stress an important point. What would happen to the wave speed if I were to increase the frequency to 3 Hz? Let me just do it and you take a look. You might want to go back a few seconds to compare with the simulation at 1.5 Hz. It would appear that things are moving quicker now, but the key is to be precise about what these things are. It's true that the red and green particles are oscillating vertically faster on average than before. After all, if the frequency doubles from 1.5 to 3 Hz, the particles complete 3 whole cycles per second compared to 1.5 cycles previously. But what about the wave speed, the speed at which the crests and troughs are moving rightwards? Our brains might perceive the wave speed to have increased as well, but in fact, it hasn't changed. If you're skeptical about this, the following should convince you. Let's pause the simulation when the green particle at the left end is at a crest. Let me now reduce the frequency back to 1.5 Hz. If this results in a change of wave speed, we should see the distance between the crest at the left end and its neighbor crest to its right, this distance here, change over time. Does it? With the help of the ruler, you should confirm that the distance hasn't changed, i.e. the wave speed remains constant. The wave speed here depends only on the properties of the string, such as its tension. We'll discuss this in a future video in the waves playlist. Now, onto the wave equation and its derivation. By now, you understand that the wave pattern moves at the wave speed v. We can find out what v depends on by considering a crest, say the crest at the left end in the diagram. This crest will shift along by a distance equal to the wavelength, and will take a time equal to the period to do this. Therefore, the wave speed is given by distance traveled divided by the time taken, lambda over capital T. Remembering that 1 over t is frequency, we end up with the wave equation, v equals f lambda. Here's a quick question for you. If the frequency of the wave doubles, but no other changes are made, how would the wavelength change, if at all? Please pause the video and have a think about this. A key bit of info in the question posed is that other than the frequency doubling, no other changes occur. So this means the properties of the wave medium, for instance, the tension of a string, don't change. As a result, the wave speed would remain constant. Therefore, in order for the product of frequency and wavelength to not change, lambda must halve. This simple example illustrates a general principle. If wave speed is constant, then wavelength and frequency are inversely proportional to each other. If one increases by some factor, the other decreases by the same factor. For instance, light or electromagnetic waves have the same speed in vacuum, irrespective of the frequency of the wave. This implies that lambda and f are inversely proportional to each other, which is something you may already know or have suspected from diagrams of the electromagnetic spectrum. Let's now move on to the final part of this video, where we'll discuss displacement versus distance and displacement versus time graphs. In a sense, Having seen images such as this throughout the video, you're already familiar with displacement versus distance graphs. All we need to do is draw in some axes and replace the string with a curve to generate such a graph. As you can see, the vertical axis represents displacement via the variable y, and the horizontal axis represents the distance or position via the variable x. As the name suggests, such a graph shows the displacement of the particles as you vary the position along the wave. Remember that capital A represents the amplitude. Some of you may have noticed that this graph looks like a cosine function, and indeed, that's precisely what captures the displacement here. You don't need to know this for A-level, but it may be interesting to you if you're mathematically inclined. Let's focus our attention on a single particle, say the green particle at the left end circled. We can ask how its displacement changes with time. A displacement versus time graph is the natural way to depict this information. We now have time, represented by the variable t, running along the horizontal axis. Recall that capital T is the time period, the time it takes for a particle to complete one cycle or oscillation. Mathematically, this graph again corresponds to a cosine function, but with time and period replacing distance and wavelength. The fact that the particle moves in this fashion means that it is technically performing simple harmonic motion, a topic typically taught at the start of year 13. So while this formula isn't required for the waves topic, you will meet it eventually. An important point I would like to stress is the following. While this graph may appear to be identical to the previous displacement versus distance graph, they have different physical meanings, so try not to mix them up. A displacement time graph depicts how a single particle moves over time. Notice the t variable and period circled. In contrast, a displacement distance graph is basically a snapshot of the wave pattern at some moment in time. Notice the x variable and wavelength circled. So, when dealing with these graphs, as long as you pay attention to the axes, you won't fall into the trap of mixing them up. To echo comments made earlier in the video, we can plot displacement time and displacement distance graphs for longitudinal waves as well as for transverse waves. To illustrate this, let's return to the sound wave simulation we saw earlier. You can see that as the particle oscillates up and down about its equilibrium position, its displacement is traced out, i.e. a displacement time graph of its motion is generated. Also, if we were to pause the simulation and examine the snapshot of the wave, we could plot the displacement of each particle from its equilibrium position. In other words, we could draw out a displacement distance graph. To finish, let me quickly mention that in discussing basic wave concepts, we focused on waves that travel along a line or one dimension to keep things simple. But of course, there are waves that spread out in 2 and 3 dimensions. For instance, this nice simulation shows a wave on the surface of water spreading out in 2 dimensions. Please note that all the concepts we've discussed in this video apply equally well to waves that travel in 2 or 3 dimensions. I'd like to thank PhET and Google Chrome Music Lab for their really great simulations that I've used throughout the video. I'll share links to them in the video description so you can check them out. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment or suggestions. I'd love to hear from you. Take care, and I hope to speak to you soon.